I have not been getting everybody's homeworks. I got like 26 of them. I know I haven't graded yours yet because you sent it in a RAR.
Oh, yeah.
Which I only have one computer that can compress a RAR.
I can change it if you like.
Like zips are much easier.
Okay. Do you want me to resubmit it?
Yeah, if you don't mind.
Okay.
Then I can grade it anywhere. So, but they won't buy WinRAR, and the zip uncompression is built into it.
WinRAR's free.
I think you told us that the first day too.
Oh, really?
Yeah.
Yeah, probably.
Yeah, but then I have to keep downloading it and the
Okay.
license.
That means I can do.
Okay. It's a pain.
I'll do that for you.
Zip is easy.
Okay.
So, but I think there was like 24 or 26 people. There's like 40 some odd people enrolled in the class. I got like 26 submissions. I've got like 13 submissions of homework number 2. Yeah.
Oh, I thought you were talking about the second one.
So did I.
Oh. Yeah, no, that'd be really impressive. No, it was only like 13 in the second one. So, of homework 1, I've only gotten a fraction of those so far. So, if I add the 2 of them together, I've got just about everybody covered, except some people appear twice. So, I do heartily encourage you. Trust me, they don't get easier the further away from the material you get. It actually, believe it or not, gets worse. So, if you go back to completely reread it, then it'll get better. But most people don't like doing that. So, I encourage you get those in as they're going.
When is homework 3 due? Or
When's what?
when should we attempt homework 3? Like when is the
Whenever you feel like it. My general advice, this is just kind of general for when you go through school. As somebody who went through like way too much school. So what I would always do is I would read the homeworks in advance. So I kind of knew what the things were, and I actually usually read them before I read the chapter. So I kind of, this is what I've gotten. These are kind of key points is what I figured the faculty member was telling me. And so when I would go through there, I'd go, do I know how to do that? So it kind of helped me to scope my reading when I was going through to pick out key topics. If I didn't know how to do that thing, then I would pay attention to it an awful lot. And then I would try to do the homework very early. It does not sound cool, but I guarantee you will do it faster. The times I did not use that method, it took me about 2 to 3 times more of my time to do the work. So you just have to ask yourself the time. Do you want to spend 1 period of time now or 3 periods of time later?
Right.
So being lazy, I'd rather spend 1 now. So that was kind of my thought on the whole thing. And then I would come in, and if I didn't get something, I would be able to hit the person with a pretty tough question so that I could get exactly what I needed covered to clarify the issue that was going on. And that really was kind of my strategy. It worked very well as I was going through. And so I encourage you, think about that. Try to get a little bit more done in advance. It will help you no matter where you go. It will also help you a little bit in your work environments. If you kind of listen in advance and you hear the scuttlebutt, they're talking about something going on or some new project, you hear about it, I would go and I would read up on any buzzword I heard on that. So that if I decide, ooh, that looks like fun, I could then strategically talk about the right subjects to the right people, and they go, oh, you know this stuff? Yeah. And then I could get into the projects I wanted to. Because they say, hey, this person knows it. Right? So you can kind of structure your career a little if you spend a little time doing this also. So it's not just a skill for now, it really is a skill for life as it goes. Cool. All right. Today we want to talk about block diagram algebra. We will be doing a little bit of Laplace transform because they're pretty linked. The reason why we want to do block diagram algebra is because basically allows you to graphically get these Laplace transform techniques from simpler components. If you think about it, one of our goals that we had was we were trying to get simplified versions of a complex transform so we could look up in a table and get the inverse. Then we could say, hey, could I start with something simple to get that equation in the first place? And you could either manipulate these algebraically or you could do them graphically. The advantage to a graphical one as opposed to a big gigantic equation is if it's kind of broken up into pieces, you can easily see what's going on. As a human being, we process things that way. So you're more likely to catch mistakes, you're more likely to see relationships between the data that's going on and therefore generate them. As a matter of fact, most major systems that are out there now, particularly for engineers to do this, will allow you to actually just generate them in the first place as a graphical entities and then get your resulting system. Sometimes you don't even see what your transfer function is. It is completely figured out for you by the system. For instance, MATLAB, which is probably the biggest one in this area, has its own version called Simulink, where you just go in and you just deal with graphical entities. And you can compile Simulink's, code that comes from it right down to Verilog and stick it right on FPGA directly from in the system. So you draw the blocks and it compiles the FPGA and you can run your system off of it. Okay? Now, is that the best thing in the universe? No, it is not the best code in the universe. Will it work quickly to get something fast that you can then look through and it'll be kind of ugly, but you can reverse engineer and make something better out of it? Absolutely, and that is entirely where its purpose is. You can do a very similar thing with LabVIEW. Most of you have had some courses over in Physics 350 and whatnot where they do LabVIEW. LabVIEW does very similar things. It's a graphical entity environment. Well, it turns out there is a mathematics behind all of these blocks, and this is actually how you can take the pictures and directly generate the equations of motion that's going on here. That's what we want to do, is how do we get those equivalents. So we're going to introduce you to a couple entities. The first one is just an arrow. Think of an arrow like a bunch of wires. Potentially a bundle of wires. Initially, it'll be one wire, because we'll just deal with scalars. That's all technically is ever required, usually of undergrads, unless you go into control systems. That's a big thing. But realize we can make it into a bundle of wires. Right? Imagine like ribbon wire or whatever. If you do that, guess what that scalar becomes? A vector. Okay? So that's all that happens is, if you think about it, a bunch of parallel wires, now all of a sudden your single signal has become vector. No words. So if I put in an X on this side, you will get X out on that side. That's all a wire does. It just transfers what's going on. Now, I'm going to draw it the way everybody in the United States draws this. I will note to you, however, that it was pointed out to me by a professor I had named Rory Smith, who was from New Zealand, that because we are on the wrong side of the hemisphere, we write things backwards. And darned it if he isn't actually right. I'll show you at the end of this, if you actually did it the other way, you drew your wires going that way, it would actually generate the equations easier. And it sounds really stupid, but it actually turns out to be the correct way to go. That being said, a few times I have taught this, and then the book is opposite, and people go online, everything they see online is opposite, and then people get confused as hell. So what I would suggest is you can learn it the one way, and then you see it and you go, oh my God, and then it's easy enough to go the other way. For those of you who really want to do this a lot, it really will make your life easier to draw it, down under style. I guess that's Australia, but New Zealand's close enough. All right, so we've got this. Now, I also could have a thing which we call simple blocks. Right? Now, a block is what you would have with all of our regular systems. I would have some type of an equation that describe what goes on inside of this. Let's say, like, initially I'll put in f of t, and I've got some signal x of t goes in, and some signal y of t comes out. So this is my input. This is a mathematical description of what happens inside. This is my output. So we've been talking about those, and we've been describing how do you get such a thing in bulk. So far, that's what we've done. We haven't really talked about how this combines with this to give you that. And we'll do that in a few secs once I introduce all of our elements. We've got another one which we call a summing junction. It's usually not written this big, but we got people far back. So normally it's about half the size of one edge of this. And I'm going to draw it large here. You'll see people do this a bunch of different ways when it comes in. I like to do putting the signs on the arrows. Okay? You will find people who will sometimes do this, and they'll go plus minus. Okay? And they have the right to be wrong. Yeah, I know, it sounds arrogant, it was meant to, just for kind of humor value. the reason I don't like this is when you go in and do this, what do you notice?
The X.
You just,
You notice a big X. So there is actually another symbol. That's this. Guess what that does? Multiplies two signals together. Straight, regular, normal multiplication.
so if you just glance at it real quick.
And you glance at it quick, you're going to read it wrong. So I really do actually have a reason for saying they're wrong. This is very rarely used. But there are some signals where multiplication, your normal multiplication, comes in. And there are some multiplicative uncertainties that come into systems, particularly in nonlinear system theory and things. And so when you get to more advanced classes, what you learned, if you learn to draw it that way, will become very difficult for you as it goes on. So I don't like that. So I use the on arrows because if you see it empty, you know automatically I'm at a sum. And what this means is, let's say this is X, and this is Y, and this is Z. If you notice this is plus and a minus on this one, that means Z is equal to X plus a minus Y. Because I put the minus there. That's all it means. Now, let me ask you a question. Do you think this would be the same if I took this same signal and went would that be the same?
Assuming X and Y are just scalars.
Would it be the same if they were vectors?
Yeah.
Yeah, because it's just a summation.
So yes, it
Oh,
is.
yes.
Right? Now, you'll see, I mean, I've seen a lot of people, so it doesn't matter the order they come in other than where those arrows go. I mean, if those arrows came from somewhere else, I mean, you got to label them correctly. But realize it doesn't matter the order they come in. Realize I could also do this. We usually come in nice orthogonal directions, but am I prevented from doing that?
No.
Yeah, I could come in from the top. Sometimes we get them coming in because we might have multiple ones coming into a summer. So it's sometimes just nicer. You usually do your orthogonal directions and then you split them and you just try to keep them as clean as possible. I have seen a number of books and things like that and over the years that have made this kind of rather confusing looking. They give you all these fancy rules. Rule number 4, rule number whatever it is they go in and, realize all you're doing is algebra. Okay? So we're just saying up algebraic rules. So think about this. All right, so we had X. I put X back up there. This is Y. Let's say this came out and went into another summer that had Z come in. What would the output be?
X minus Y plus Z.
All right, X of t minus Y of t plus Z of t. Would that be exactly the same as if I switched Y and Z?
Yeah.
This is the same as X of t plus Z of t minus Y of t?
Yeah.
But wouldn't that therefore be, here's my X, here's my Z, minus my Y?
Yeah.
Yes, it is. So notice, guess what I can do?
Move things around in your drawing.
I can switch the order of the summers. Okay? You know what that means? That's called commutative property.
What's that?
Okay? So people give it all kind of, they'll tell you, oh, say it's this rule, whatever. Just realize it's just algebra. It's commutative. Addition commutes. So it shouldn't be too surprising that a summer, which is addition, commutes. And notice I also group them together. What property is that? I can group them together how I feel like. Associative. I could also do this. This is also equivalent to X comes in, Y, Z. The output of this is x plus z minus y. So I can associate them how I want. I can commute them how I want. That's not surprising. This is just saying when you're adding numbers together, addition, commutes, and associates. All of a sudden we draw it on pictures and people go, whoa. Okay? That's all it means.
Hold on there, champ.
I know, yeah. You know, I mean, but you've been doing this same exact thing since elementary school, right?
When you're dealing with the multiplier, though, it's not the same because when you're dealing with vectors, you can't.
That's true. Once you go, so you've got to remember what's the entity type I'm dealing with.
Yeah.
This is why I always say the first thing you should do in any problem is ask yourself, what is the thing I'm dealing with? Is it a scalar? Is it a vector? Is it a matrix? Right? Is it a tensor? You need to know what type of thing this is. Once you know what type of thing it is, now you can start doing something with it. Right? But we said all we're doing here is we're doing the equivalent of your normal algebra on these functions. So therefore it should follow normal algebraic rules. Make sense? Okay. So don't get surprised. I'm not going to draw a million. Like if you look online, I'm sure if you look up for these rules that go on there, they'll have pictures. And they'll give you tons of rules that show you these things coming in from different angles and saying it's always the same. You should realize they have just wasted a lot of paper to tell you that addition commutes and associates. Okay? Don't get surprised by it. A lot of people get very confused by it. And they get scared, how do I switch? But really, it becomes very important to us to just realize it's simple and treat it that way.
Does anybody ever draw the plus and minus signs on the actual letters themselves rather than like the signal name?
You can. However, I would suggest you don't do it. And this is the reason. What you're saying here is you're saying there is something that generated this. It didn't generate minus this. And then you're saying you're feeding it in negative.
Okay.
That's going on. And that becomes important. We often do, for instance, like negative feedback.
Yeah.
So on a line that's coming backwards, we'll often put that one in to let you know it's a negative feedback line.
Oh.
So that way people go, oh, okay, negative feedback tends to stabilize systems. I feel better about it. So it allows people to check those very quick. It's another one of those quick checks. If you don't see that, then you now have to go back and check. And, you know, technically speaking, I could, you know, stick that there. It's perfectly the same, right? Plus and minus y. But I could redefine this as like y bar, and y bar is minus y.
Yeah.
Right? So now you just look at the thing anymore and you're like, y is coming in positive, right? It could be very confusing. And then you have to go look up some definition, which is invariably inside a thick paragraph written in a badly readable font. Okay? And now it's a pain in the rear. You've lost the whole benefit of the picture, which was to allow you to quickly check and do, you know, hey, does this make sense? So the reason why I would argue for this, technically you could. Right? Now you have to think of what's going to make my life and other people's life easy. And I would submit this makes it a little easier. I will often not draw the pluses on the other ones, and you will see this. I will usually only draw the minus when there's a minus. This has both advantages and disadvantages. Life's a trade-off, right? The advantage is the minus sign becomes more apparent to you.
You also don't
So therefore it jumps out.
You don't have a slot.
You also
plus
don't know if I
like
forgot.
Yeah.
Yeah.
That's the disadvantage. So it's more obvious in one sense, but it's also easier to screw up.
So is this a graphical representation of the equations that are going into a microcontroller? Or, okay.
And the entire system.
Okay.
Right? Usually we'll draw them with the microcontroller down below on the feedback line. We'll have the main system, whatever you determined. You know, we've talked about how you can get the equations of motion for like a robotic arm using Lagrangian
And now we're
mechanics.
actually.
So that would be the actual system. So then you can actually put in your controller's equation into the actual system and see what does it make it do. And you can find out the effect of that controller on that system and find out what the output would be.
And then you can calibrate from there too.
Exactly. You know, it allows you to tune, it allows you to simulate, You know, you can validate not just your design, you can also validate your control. If I give these commands, what does it do? And anything we can simulate before we actually build and run, going to save you A, a bunch of money, you know, B, a whole bunch of time. You know, plus potentially your job, because if you actually send a bad signal and it destroys the system, you are probably not going to make it through that one.
Yeah.
All right, so far so good? All right, now, these ones, honestly, if you understand what happens here, you can pretty much get everything else.
Yep.
So I want to just cover a little bit what's going on here. Because this is not quite what you would expect. The question is, how do I get what y of t is? All right, this is some function g of f and x. The question is, what is that? What is the g? What does the box itself represent? Does that make sense?
Yep.
Well, my question is, this is, what is the system? What was the input? And this is, what the heck does the box mean? How do they get combined? They get combined by a type of multiplication. Now, if you remember up till now, we've talked, there's lots of different types of multiplication out there. Well, we're going to get a new type of multiplication, which is actually an old type of multiplication, and we'll show in a sec, which we call convolution. So this is where convolution really kind of comes into its own. Convolution you can think of as the operation of combining an input together with a system description at a time. Now, I say this is, before I give you actually the definition of it, I want to show you how this is pretty much exactly something you've already known for a long time. How many people know how to multiply polynomials? They have a pretty universal agreement on this one. Right? That's all convolution is. If you discretize this, convolution becomes polynomial multiplication. So this is why I say it's something you're familiar with. However, how do you multiply really big polynomials together? What do you do?
Wolfram alpha.
Yeah. Okay, so how does Wolfram alpha do it?
Big foil.
Well, no.
Foil's a pain in the rear, though, isn't it?
The nested functions?
You know, we can rewrite something in terms of nested and away we go.
Don't they look
Wouldn't
at
it
the
be
series?
nice to have a nice, simple data representation for a polynomial? And then an easy way to multiply and therefore also divide them?
Mm-hmm.
Okay, so let's consider a, fairly simple polynomial, which you guys will supply. You're going to give me two of them. So give me some polynomial.
What
I don't
order?
care what it is.
What order? Do you care?
The bigger you make it, the more I'm going to write, but I don't really care. I'd make them different, maybe like one a cube and one a square or something like that, or,
X to the
like
third.
one quartic and one a cubic. I don't really care. Somewhere in that zone. Otherwise, we'll just spend all day.
X to the third minus 2x squared
X to the third minus 2x squared.
plus 4x minus 1.
Awesome. I need another one.
X squared minus 5x plus 10.
Plus 10? What did you say minus? I just didn't hear.
So plus 10.
Plus 10. We okay with these?
Yes.
All right, now normally what you would do is you would walk through, and you're going to go through and you're going to multiply x squared times each term, right?
Yeah.
This is kind of like what you've always learned. If you think about it, this is kind of like what you normally did with other number areas where they go and you go, 10 times each one of these, and we would get, 10x cubes minus 20x squareds plus 40x's minus 10. That's this times those. Right, and then you could just do the same thing. 5x times all of them, it shifts them all over, right? So I get 5x to the fourth minus 10x cubes. Right? Let's see, plus or minus. Oops, I should have minus, right? I forgot that one. Minus 20x squareds.
Plus 5x.
Right, and then plus 5x. And then I've got this one. It's just kind of funny that we ended up with your random one. I mean, if you guys hadn't given this to me, I'm like, dang, it would look like I was cheating here or something.
Audience glance.
Teamwork though.
We're cheating.
I know, good job. It just kind of caught me surprised that it worked out so easily. X to the fifth. And I know this isn't the normal FOIL thing that most people do, but I want you to see it really is just multiplication in a sense when you're grouping them. It'll also make a lot more sense when I go to show you our shorthand rule for doing this and our easy way of writing these. This is an ugly way to write those for a computer.
Right.
Okay, so then we've got plus 4x cubed and then minus x squared. All right, and then you could just sum them up. Minus 10.
I've never done it this way before. I'd like it more.
Yeah, it's the same dumb thing you've
Yeah.
always done. But realize it. This is why I always make the statement, there's a ton of ways to do anything. Find which one makes sense to you and go with it. So this is minus x squared. And this one is what? 24x cubed minus 7x to the fourth, x to the fifth. All right. So far, so good?
The x squared.
X squared shouldn't be.
41.
The 20s don't cancel. So negative.
Oh, they're both negative. I had the number in my head
So
of,
it's minus 41.
yeah. When I had my signs flipped, I had already pre-calculated in my head. And I wasn't actually adding, I was just remembering. Just the danger of remembering wrong. Right? So, but this is fairly simple. It actually organizes them fairly nicely too, and you can actually see your FOIL method if you really want by doing it. This is closer to what we're really going to do though. Now I submit to you, an easier way of doing that is, what if inside of my line, I'm going to make a vector. I'm going to call these my constants, and these my x terms, and these my x squared terms, x cubed, so on and so forth. So this one has for a constant minus 1. There. And then the x is 4, and the x squared is minus 2, and the x cubed is 1. Now realize you could flip this definition, you could write the whole thing flipped.
Yep.
It's not really a problem. As long as you know which way you're writing them, who really cares? Now if you want to think about this, the position inside the array tells you the exponent. Right? This is the 0, the 1, the 2, the 3, and that's just the exponent of x. So it's all very nicely encoded at that point. Following that rule, I could easily write 10 minus 5, 1. They're not the same size, are they? Does it matter?
0. Yeah.
That one has 0x cubed, doesn't it?
Yeah.
And if you start thinking of these as displacements, what if I had something like, plus 1 over x? We don't, but I mean, imagine I wanted to. Most people would look at this and blow a socket or something. Realize you don't have to, you just have an extra term on the end, who cares? Right? It still fits within that rule,
Yeah.
but it usually causes people a problem. But here all I have to go is to the minus 1 position. So I have 0 of the minus 1s. So I could extend these as far as I want in either direction by adding zeros.
Yeah.
0 padding is perfectly legal. It doesn't change the vector. So you can resize them as you want. So the size of the vector isn't as important, just the non-zero portion of it is. Now anybody go through like network theory or graphics theory? We have names for these type of ones. We call it the support of the function. The region where it's not 0. So if you ever go into visualization theory or all kinds of other stuff, the support is the region where the function is non-zero. So what matters to us, I mean, I can extend zeros as far as I want, but those are kind of boring. So I only write the part where it's non-zero. That concept becomes very important when you go into like wavelet theory and stuff like that. All right, so far so good. Do we agree this is much simpler to write in a computer?
Yep.
Okay, now the question is, can I do something with it? Well, could I add them together easily? Yeah, all I have to do is just add the relative components, and that is what you have for normal polynomial addition. Now you have to ask, what am I going to do for multiplies, though? Now what I want is, I want the highest power of this one multiplies the highest power of that one, doesn't it?
Yeah.
Right? And then this one multiplies that one, and this one multiplies that one. But they're kind of crossed over, aren't they? And then this one's going to multiply that, this is going to multiply that, and that's going to multiply that. it's crossed over again, isn't it? It's almost as if, as I wanted to write the multiplication for this, I'd better off writing it 1 minus 5, 10, right in the opposite order. Then this one multiplies this one to generate the first number. And then this one multiplies that one, and this one multiplies that. Nothing crossed. Do we agree that that's kind of nice and cool and simple? Yes?
Yes.
That's a nice feature, isn't it? So that's what we're going to do. We're going to flip one of the two of them. You clearly don't want to flip both of them. Then you'd be back to the same spot you were. This is going to become very important when I write the real version of convolution. So it's not an extraneous idea here. All right. Then what I have to do is I have to just keep, these two multiply those two, and then these three multiply these three. So then I keep shifting, right? Shift and multiply. So write one reversed, shift and multiply. That is what we mean by convolution, which is polynomial multiplication. So let's see how it works. I'm going to leave a little bit of room here. I'm going to write my to be shifted one up here. 1 minus 5, 10. Realize it doesn't matter whether I write it top or bottom. And what I'm going to do as this goes in, I'm going to take them, multiply, and underneath where this one is, the leading one, I'm going to write my answer. Fair enough? All right. So obviously with the 0 extends, there's theoretically zeros here. So if it was shifted over this way, it would have just been multiplying zeros and I'd get nothing. So here I go. 1 times 1 gives me 1. Everything else is multiplying zeros. Right? So nothing interesting happens with those, so I don't have to worry about it. Fair?
Yep.
I'm not going to write all the zeros as we're going. I'm just going to keep writing my interesting numbers. Remember, I write it underneath the 1. So I've got 1 times minus 2 and minus 5 times 1. So minus 2 and minus 5 is minus 7. You just add them.
Yep.
Now you might ask, why did I do that? Well, this is 1, minus 2, and minus 5.
Yeah.
It's not going to be an accident. You're going to watch me build this chart. Just one at a time as I go through. But I just got minus 2 and minus 5 gives me minus 7. That's the next chart. So I've now done that and that. Remember, this is my highest order power. This is my second. 1 minus 7. First two done. Okay? Neat thing is, if you stop early, you get the high order powers too, which are usually the ones that kind of blow up in your face.
Right.
Kind of another neat feature. All right, we good with this one? We shift again. 1 minus 5, 10. 1 times 4.
4.
Minus 5 times minus 2.
10.
10 times 1.
10.
So 10 plus 10 plus 4.
24.
10 plus 10 plus 4 gives me...
Witchcraft.
Realize I don't have to do any of that fancy stuff. I don't have to remember any of the stuff. All I got to do is keep their position right.
Don't even have to figure out which order you're at.
Yeah, isn't that awesome? Isn't that so much damn easier? Can you? I mean, you could program this very easily in a computer.
Yeah. Shifting.
Okay. Then we're going to show you. This ends up being, since we have to shift and do all these multiplies, it ends up being an n-squared algorithm. Just a general question. There's a decent number of CS people here too. Anytime you see an n-squared algorithm, something should jump to your mind.
You're running high.
Well, you should
Get rid of it.
try and do better.
You would like to do better, right?
Yeah.
If you see an n-squared algorithm, there's almost always a thing you can do that'll get you to n log n. Divide and conquer. The second you see an n-squared algorithm, you should just automatically go divide and conquer. And it will, you can almost always find something that will take an n squared to an n log n. Right? Sorting. In general, you write bubble sorts, you write the silly first idea sorts. What do you get? N squared. And then you go, it's an n squared, I can divide and conquer. Quick sort. Boom. N log n. Right? Or merge sort, another divide and conquer, and you get n log n. So this is kind of where that idea came in. That's right. It's algorithms, but you should realize this. For us, convolution, it's going to turn out there is a faster way of doing it. It just goes through what's called the fast Fourier transform, which will turn it from n squared into n log n. Okay? So this is where we're going to want to do this, and it turns out to be the fast way of going. It's exactly the same as algorithms does. Okay, so far so good?
Yep.
Shift and multiply. 1 minus 5, 10. That gives me minus 1, minus 20, minus 20. Minus 1, minus 20, minus 20. What? Not only does it give you the same answer, it gives you the same exact stupid table. I'm just generating one at a time. Shift and multiply. You keep doing it until things stop lining up. Right, this one's no longer there, which tells you you're at this point here. This is why the leading one doesn't line up with anything anymore. It generates a 0, which is right there, a 0. Right? I get 5 and 40. Right? 5 plus 40, right under the 1, 45. Shift and multiply. Minus 10, right underneath the 1, and minus 10, write it in. Any shifts after that, I will always be multiplying a value times a 0, so nothing more will be generated. That makes that one my least significant bit. I now have them. I always said, there's my constant all the way through. And if you notice, 1, 2, 3, 4, 5, 6. Right, that's the number of terms that are in here. This one had 4, that one had 3. The size of this vector is equal to the size of that one plus the size of that one minus 1. Size of your first plus the size of your second minus 1. Always, always, always. Gives you the size of that one. So by knowing it in advance, you might say, well, what do I care about that? Well, do you want to actually do this by hand? You're going to write it as a computer, right? Wouldn't it be nice to be able to declare the size of the vector for the solution in advance?
Yeah.
So by looking at your initial vectors that are coming into this, I can automatically size and I won't have to dynamically reallocate. I know the size of the solution in advance. So that's why you care, so that I can declare in advance for my routine to do this. Good?
Yeah.
Isn't that kind of nifty? Right, it's what you have always done made easier for a computer. Polynomial multiplication is now trivial. Right? I mean, this is not necessarily the most elegant way for us. Right? Honestly, I think this is probably the easiest for most people to see, which is why nobody ever shows that. Right? They usually do FOIL because then it looks complicated and you believe there was a reason for taking it.
Plus it has a acronym. Acronyms are famous in school.
For foolish, obfuscated, intolerable lies. I don't know.
Yeah. Doesn't matter.
Just make sure, so when you shift, you multiply the add down, multiply across.
Yeah, you just each time. Yeah, you just each time you shift, you're going to write it under the leading one, what the answer is, and you just multiply the corresponding original terms and sum up what their products are. So if you want to think in 310 terms, this is a sum of products rule, and there is correspondence to that as well. Okay, so it shouldn't be too surprising. There is a sum of products form in larger algebra too. This is why I say there really are only a few ideas. Realize digital logic is a footnote on algebra. We're just showing you cool rules that do it easily. Neat ways to look at it. Okay, so we're good with that. So what we want to do is then say what this is. Now, we said it was a sum of products, right? Once I go to continuous time, a sum becomes an integral. All right, so it's going to be a sum of products. Well, it's going to have to involve f times x. One of them we kind of leave fixed. Remember, I can't just call it the same thing inside because I'm doing this in terms of t's, so I've got to make sure I'm integrating across those. This one right here has to be a shifted version, but it's got to be flipped. So it's got to be flipped. You flip it by negating your axis, right? And the only variable direction I can shift in is the t dimension. That's what we did here, right? We shifted it in the polynomial's direction, but now our polynomial is time. So the only thing I can do is shift it in the time direction. There you go. So if you remember what you did and just turn it into it, it turns out that this is just the extension to continuous variables of what you did in discrete variables for doing polynomial multiplication. And it turns out that this is how pretty much everything you can imagine the world works. Right? The light coming from here goes through an atmosphere which has dust particles and all kinds of other stuff. So it scatters it. Well, those dust particles have a distribution called a Gaussian distribution of how it scatters the light. So you have some shape pattern or a function that describes the shape pattern of your light. You know, let me call this my scattering, right? So I've got some function that describes how it's scattered as it goes through time. And I've got something that describes the pattern of light that's going through. If you do that light pattern convolved with your scattering matrix, you will get how light blurs. If you put a particular voltage signal into a motor and it has a function that describes from voltage to torque, you give it a particular pattern of voltages, the output is that function describing the pattern of voltages convolved with the function describing the voltage to torque equation. Right? It works for light to make pictures, it works for electrical motors, it works for mechanical arms as it's going on. You have the system from Lagrangian mechanics that describes how the arm moves. You have some input function that describes how you're commanding it to move. Convolve them together, you get what it does. That's all it is. Okay? That make sense? Mm-hmm. So that's why this becomes so important to us, because it really is what happens in life. Therefore, that's what happens here. Right? I take x of t, convolve it with f of t, I get y of t. But that's a pain in the butt, isn't it? So we've got to say, is there an easier way to multiply that?
Of course there is.
Yeah, and I've already mentioned one of the things that the fast Fourier transform does that night for discrete things. Therefore, you would expect the Fourier transform probably does something neat for us overall. And indeed it does.
Yes, we can.
So this is one more little side note. Because from now on, we're not going to write f of t inside here. We're going to write everything in Fourier space. And you're going to see why. We've already shown that differential equations are nicely handled by it. It turns out it's going to make convolution very easy too. So therefore I can ask, what is the Laplace transform of f of t convolved with x of t? Make sense?
Yep.
All right. Let me give myself one more room. All right. Laplace transform goes from 0 to infinity of whatever you want to transform. In this case, it's f of t convolved with x of t, e to the minus st dt. We agree?
Yes.
But this can be described by an integral. Integral 0, or sorry, minus infinity to infinity of tau there's convolution, and that finishes up Laplace. We agree?
Sure.
Yeah, didn't we used to have?
X of t.
Oh, did I
minus
forget
tau.
my X?
Yeah.
Oh, I wrote its things. I didn't write the.
It's just implied.
But
No, yeah, I agree. I have no problem with that. I forget to write things all the time.
You're not alone.
so if I forget to answer a test question,
Then I mark you off because I'm a hypocrite.
Unless you can fix it.
Just like my professors before me.
dang it.
He gives you a chance. He gives you an hour, however long the test
That's
is. to
why,
correct it.
you know, that's why you ought to go back and look at it.
Oh,
Is there an X or?
I'm an honest hypocrite, though. So,
at least
It's an X. There we go.
all right, we good?
Is that an X or is that a multiplication?
It's an X.
It's an X.
It's an X.
As a general rule, I do not write multiplication signs.
Yeah, I hate that.
If it's normal multiplication, I'm not going to write multiplication. If you actually see something from me, right, it's usually telling you something special is going on, right? Because we have normal multiplication, but we have also dot products, we have cross products. You now have convolutions. Anybody know any other multiplies? There's another big one you use all the time.
cross.
Multi just
Oh,
has-
both sides, yeah.
Correlation, if you ever do
Oh.
probability and statistics. What's the correlation of two variables? That is a type of multiplication. It's done by a 5-pointed star.
Still take like this.
Okay, so there's all kinds of ones. You also, less known ones, you have the Kronecker product if you get into
Okay.
relativity and stuff. Yeah, there's a lot of these variants. But to avoid any confusion, because now what the heck do I use if I want just regular multiplication?
Nothing.
Yeah, because
Yeah,
not to
nothing. You're exactly right.
Yeah.
It's if I meant the normal thing, I'm not going to tell you. It's assumed.
Yeah, because over the years we've seen like a lot of these already just for regular multiplication. A dot, a star,
Because
cross.
they actually reduce down. If you take the dot or the cross
Right.
products for
for
scalars, it
scalars,
reduces to
yeah.
normal multiplication.
Right.
What if you were doing, the whole problem with polynomial multiplication, but you only had constants?
Yeah.
It's normal multiplication.
Yeah.
So that's the neat thing about these. They reduce to normal multiplication when you're dealing with, removing the complexity of their thing. You drop down to constants and blah, 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 blah.
But then most people assume when you see that one of those, oh, I'm not dealing with scalars anymore.
Yeah, so now I've had confusion. So I will not write that. So if you see an X, I mean an X unless I mean a cross product. In which case it should be apparent, from the context, hopefully. All right, now, the challenge we see in this is, well, first off, it looks ugly, right?
Yeah.
But we ideally, right, when I've got integration, I need to either be able to solve one of them, right, or separate them out so I can do them in parallel. Now, in this particular case, right, this is on the internal parts of it, and it's going to end up giving me something of t. I'd ideally like to be able to switch the order.
Yeah.
That would help me a lot as it's going on. Now, when we're doing these, I'm integrating my tals. Technically, I'm supposed to integrate my tals across the entire whole area. But this thing really just ends up functioning. These ones aren't defined for negative time, for instance. All of our functions are positive time. So really, as far as our time is concerned, you're only really going from 0 as it's going on for tau. Just because our functions, we have said we are not going to define them for negative time. We'll give you initial conditions as it goes. That was the assumption of the left-hand transform as it goes. And then on these, they only go up to the length of time that the whole system's in, so we can actually just do this from 0 to t. Because that's the length of the function as they're going on, the t that's across it. So you will often also see these written this way as it goes. Right? Because there's just nothing, it's all 0 after that. That's all we've done to observe it is, one of them cuts it off. This one right here is all zeros in negative time. So it forces that. This one is all zeros greater than t. Right? Because the smallest or the biggest t minus tau can ever be is if tau is 0.
Which is t.
Which is t. So there's just nothing above that.
Yeah.
So by changing this, I haven't actually changed anything. I've just observed what I told you with the other ones. It's all zeros past that. So I'm only going to consider the region of support. So if you ever see on there, they often give you that definition and they write this and nobody ever tells you why. Okay, now you know why. All right. So we now want to switch the order of integration. We did this, I think, a time or two ago. I forget, either last class or the time before. We switched these and we said, it's running from, tau goes from 0 to t. All right, so if I've got, say this is tau and this is t as the variables. My tau is running up to t, so you got kind of like a constant line. So I'm saying tau is running from 0 up to whatever t is. That's how long you do taus. And the t runs from 0 to infinity. So I'm up here. So when I flip the order of integration that's going on, t has to run from tau to infinity.
Wow.
Does that make sense? This is just changing orders. People are looking at me like I'm from another planet. We all agree with that, right? I mean, you gotta, not only are you doing when you flip the integration, you gotta do it over the same region of space. So this is the region we discovered we were operating on. So that's the region I have to integrate over. So it's running from, and remember this line is t equals tau.
Which is why I just go straight
Right?
from the line.
So my first value of t at any particular point in the middle has to start at whatever the tau value is at that point. So over here, that means I'm now running my integral. So the inner integral now runs from tau to infinity. That's going up. And then I have to run across all values of tau from 0 on up. So this has to go from 0 to infinity. And it's t on the inside and tau on the outside now. So far, so good?
Yep.
So doing that, now I've got my order of integration changed. F of tau, x of t minus tau, and e to the minus st. Now I'm going to do another trick. I don't like that.
Too much tau?
Kind of ugly, isn't it?
It is.
So I'd like to get rid of it. So I'm going to call T1 to be T minus tau. Fair?
Yep.
And I'm going to use that as a replacement for T.
Okay.
Okay? So that means I've got to find a replacement. This obviously will nicely handle there. I've got to find a replacement here. I got to find a replacement here.
Right.
What's the derivative of T1?
DT1.
Well, tau is constant because I'm only considering it with respect to t, so it's just T1 is dt.
Yeah.
And the derivative of a constant, which will be 0, because I'm just considering it on the inner one. The outer one is constant inside. That's why we flipped the order of integration, so that I could do this.
Yeah.
So I just have dt1 equals dt. Okay? Okay. How about just t?
T1 plus tau.
T1 plus tau. I can stick that in, can't I? Tau x of T1 e to the minus s times T1 plus tau times dt d tau. I submit you are almost done at this point.
Should that be dt1 instead of d tau? Okay.
It is.
My bad. My mistake.
I'll try to write it in normal colors. Darn me writing in ultraviolet. All right. The reason why I say it's almost done is you notice the distributive up here, right? So I can distribute with the exponents and just rewrite this. ST1. We agree with that? This is distributive. Now notice, I've got some stuff that just involves T1 and I've got some stuff that just involves tau. And I'm either integrating on T1 or tau. They're fully separable at this point. So I separate them. As it goes on, and I've got this whole lovely thing, f of tau times e to the minus s tau, and that's d tau. I can pull the tau through. Now I'm going to fully pull them through, and somebody ought to complain at me, and I will slough it off. But you have to at least complain at me, otherwise it's no fun.
I'm complaining at you
Why are you
For what
complaining?
reason? Yeah.
because you have decided to change your limits of integration without telling me.
Yes,
I'm going
I
to be annoying
did.
mathematician and say, why?
Yes. So, and it's easy to say why. Can anybody see why I can do that?
Because when tau is before
Tau is
zero,
not involved inside your other one.
Your functions are zero outside this integral region. Right?
I can dig it.
Remember, I'm integrating this on T1, and we mentioned the fact when I originally started out, I was originally at minus infinity to infinity as it was going on. We said outside the region, if it was less than zero, if it was bigger than t, it was zero. So when I was doing this thing and handling the limits of integration here, one thing, I mean, I was being strictly correct with dealing with integrating over the region, but realize it still would have worked out if I didn't, in this case only. And the reason is because it's zero outside. And that's what we said, the functions are zero outside. They were finite duration. If you don't have finite duration functions, you can't do that. But I do. So since I have finite duration equations, I can be cheesy and just go, well, I can add in the integral from 0 to tau of what's inside, because what's inside is 0. So what I have noted to you is I can add a whole bunch of nothing. Now, the question is, and this is, remember I've often told people there's two real tricks in math. Multiply by 1 or add nothing. This is the add nothing trick. Right? But you just got to add very clever, good-looking nothing. Okay? You strategically have to put the nothing in. So I very strategically did. Anybody see why I want to add that particular block of nothing? Because that's just the Laplace transform of f, and that's just the Laplace transform of x. This is s. But I didn't write it because that's normal multiplication. So the Laplace transform turns convolution into normal multiplication.
Diggity.
That's a particularly nice property. Okay. Now, computers can calculate the Fourier transform, which is related to the Laplace transform, using the fast version in n log n. Regular multiplication of two numbers when you have a whole bunch of them in an array is just the size of the array. So to do the transform one direction is n log n. To multiply them is n. To pull them back is n log n at worst. N log n plus n log n is n log n. It's your worst. So that means I can actually do convolution faster by transforming than I could if you actually just did it straightforward. Okay? This is part of why we like it. Convolution is kind of complicated, but if you take it into transform space, it's just normal multiplication. You don't have to worry about that. So if I bother to write these things here in the time domain, I'm forcing you to deal with convolution. However, if I were to change this and now write this like this, then you could just write the Laplace transform of that. It's much easier, isn't it? So I admit it was a big diversion. However, it's a big diversion that's going to save you a lot. You will notice anybody with any sanity never writes this in the time domain. We always do it in the Laplace domain. Because the actions for us are much, much simpler. So we just convert each individual block into Laplace, which can be done very quickly, and they're very small, so it's very, very fast. Do all my actions and then invert. Make sense? Mm-hmm. All right, so let's actually try something big. All right? So let's say I have some reference signal that comes in. I'll give it to you in the S domain. And I'm trying to make this really kind of ugly looking.
Is that minus for the line coming from top or from?
Yeah,
okay.
for the one coming.
Okay.
And we'll put, let's say, H1 of S. And this is my output X.
God.
Sufficiently ugly looking?
Yes, sir.
Beauty is in the eye of the beholder.
Not bad for a first one, right?
No, not bad at all.
Okay. So, what we want to do is see if we can simplify these things up. We would ideally, our end goal is to have something that does this. R of S goes into something and comes out as X. That's what we want. So we've got to just graphically, and by learning kind of the rules of how graphics work together, we'll have to develop one more little thing on how do we handle feedback, but you can actually develop that. Right? I don't make it a separate rule, although I guess you could if you wanted to. It's actually a simple little algebra picture. Make sense? Mm-hmm. Okay. Actually, is it okay if I make this even worse?
Sure.
We got space up here, it hopefully won't ruin anybody's thing. But I can do this, right?
No, I think it's ruined.
Oh God, it's ruined. Lit on fire.
That's even better, isn't it?
Yeah.
Better.
That's the way to use to describe it.
Yes.
What? No?
All right, why not?
You know, let's put something else in there too.
No.
Yes, yeah, encourage him. Yeah, that's
We spend all day creating the problem and not solving it.
Okay. So we're okay so far, right?
Yes.
Okay. So now we want to see what type of stuff we can do. First thing I'd like to do is to these are kind of like loops that cross each other,
Yeah.
right? So they're not nested loops, and right, we don't like things that aren't nested. The first thing I'd like to do is remove the unnesting. So I can do it on this side fairly easy, right? What can I do to this side to simplify?
Combine those two.
I could combine them. I could also switch their order, couldn't I?
You sure could.
It's just addition. So if I wanted to, I could do this without any problems whatsoever. We all agree?
Yeah.
Okay, that means I've got a loop right here, don't I?
Yeah.
Okay. So I can try to reduce this whole loop into one block. Okay, so let me call this Fred. Right, Fred of S.
Okay.
Right? Can anybody tell me what's over here?
Almost.
If this is Fred coming into H1 of S, what is it?
Fred times H1.
Capital Fred.
This has to be H1 of S times Fred of S. We agree? I'm just going Fred this signal right here. Yay? And the signal coming in here, I can just call it Y. Just for a name. Huh? All right. Now, this one right here, this Fred of S, what's its equation equal to? Well, it's Y of S minus H1 of S Fred of S. Do we agree?
Yes.
Fred is the summation of Y1 and minus H1 Fred. You all agree?
Mm-hmm.
But I want Fred. I got Fred on both sides. What should I do?
Divide.
Take Fred to the other side.
Yeah.
Right? So what I've got is Fred plus H1 Agree? Can't I undistribute Fred?
Yes.
Yes? But I just want Fred on this side. I don't want this
Divide.
junk.
Yeah. Divided by junk.
So that means Fred of S has to be Y of S times 1 over 1 plus H1 of S. Right? So, but that means this right here that's going on, I could replace it by this whole thing. That means this over here, H1 times Fred of S, is just H1 times this. Right? So, H1 times of S times Fred of S is just H1 of S. Right? Now I know what this is. In terms of one thing multiplying another. The input multiplying something else in the Laplace space. But multiplication in Laplace space is the equivalent of convolution in time, which is an input going through a system. But we know that's the input, that must be the system. That is your system. So my system, oh, maybe I should make that block a little bigger so it's readable. Right? Algebra. This is why we like negative feedback. Is that negative feedback generated this plus? Because remember, it was negative feedback, but I took it to the other side, which made the plus. If I had positive feedback when I took it to the other side, it would be minus.
Change your system of grill, right?
Yeah, and this is why it would grow. How big is this? Well, assume H1 is positive. Fair assumption, right? My system is not negative. The system doesn't swing negative as it goes. Size of the top versus size of the bottom. Well, the bottom is the top plus 1. So the bottom's got to be bigger, right? So this is a fraction where the top is smaller than the bottom. So how big is it? Less than 1, which means it's shrinking. That's why negative feedback stabilizes your system. It causes it to shrink. That's in a nutshell why it works. Negative feedback causes your system in magnitude to reduce in size. So as time goes on, it's going to get smaller and smaller. That's stable. If it starts out and gets bigger and bigger over time, that's unstable. So far, so good?
Mm-hmm. Yeah.
All right. So, now what do I need to do?
We can break the bottom branch.
Well, what about your top, the 2 in parallel?
Yeah, that's kind of ugly looking, isn't it?
Yeah.
Yeah.
For your wire service, the H1 on top of it, I understand that you have the one over.
It's kind of
Can you speak a little louder?
Oh, the H1 in the last term? Or the H1 over?
Yeah.
Yeah, what the H1?
It's H1 of S over 1 plus H1 of S. The 1 came from that feedback line,
Right.
which I had nothing on the feedback line. So that's actually, it's got a special name. It's called unity gain negative feedback. And that's where it came from. If you think about it, it comes technically from here, which is the fact this side, which was the input line when I had the feedback line coming in, was the thread. I took this one over, so I get 1 plus H of S. The 1 was the signal itself. And then I gave it negative feedback, which is where the plus H1 came in. Make sense? Evidently I talked too long. I'm killing the batteries.
No.
Okay.
This thing just sucks.
All right, now,
The guy
what's the
playing.
challenge here?
Parallel.
Right? And that's a little bit, and we go, oh, and you know, this one cuts out of the loop and this one cuts down, so we've got to manipulate that. There's a couple ways you could think about it. I could either take this line and move it before here. That'd be fine, wouldn't it?
I'm sorry, you said...
If I could take this line and I could move it back over here, that would be fine,
That
wouldn't
would
it?
be really nice.
Right? That'd be one way. Or I could take it and move it past here. I could do it. As long as either of those cases happened, I'd be fine, wouldn't I? So, the easier of these two is to move it before. Right? Now, if I moved this line before,
You would need H of 2,
what would be missed
the H of 2 of S.
on this line, right?
Yeah.
I shouldn't go there then, because it's coming out. Right? I'd be missing H of 2. So if I just copied it down, have I changed anything?
No. Not in the slightest.
Both lines both get scaled by H of 2. Maybe it's some extra hardware you have to build, but heck, we're only partway through the finishing this up.
We're not building it every step of the way.
Right. But if you think of it in those terms, I haven't changed anything, have I?
Actually, we have to, because we don't have a whiteboard.
Yes, well, that's your problem.
It is.
You also have a camera, so you can always go back and rewatch it. Okay, we good? Does that make sense? Well, now think about this. What I've got is a series of things. Well, H2 just goes into H3. I can combine those together, can't I?
Of course.
One thing flowing into another. One thing going into another is convolution in time, which is
Oh, multiplication.
multiplication. So, make my box a little bigger, which you get to do by completely rewriting.
Well, sometimes I take sections of it, but yeah.
Huh? Because remember, we said one thing, that's the thing we took the huge diversion on, right? Something goes into something else, it just becomes multiplication in the S domain. So if you see a whole bunch of things in series, you just go, oh, it's multiplication, who cares? It's about as nice as it gets. Now, we have this thing though, right? I've got feedback.
And it's negative.
All right, and it's negative. Negative feedback is good.
Oh, damn.
So I'm going to do the same exact thing we did before. You consider this point right here. Eventually you will notice there is a lovely pattern to this, and you won't have to ever do this again. But I just write this as y of s. Y of s is equal to what?
Sorry.
Y of s
Sorry, slowly drawing.
is equal to
R of S minus
That's minus H2S.
is it okay if I leave the s's off?
Yeah.
We all feel comfortable with it, because it'll save us like a whole bunch of space.
So it's just supposed to do that.
So y is equal to r minus h2, h3. That gets me back to here. All right? And then this, it's just in series, so it multiplies. Times y. We agree?
Yes.
This times that, they're in series with each other. Times that, they're in series with each other. I want all the y's on the same side. And I distribute. We agree? I just did 2 steps, so hopefully
Yes.
you're comfortable with me jumping. Good? So what do you think I should do? Divide. I want y by itself. That's just 1 over this mess. Now if you notice, it's 1 plus what was on the feedback line times what was on the system line. But this is the input times the system. So that must be the system. Right? That's the net system to give me y. To give me the output, I have to multiply by that, because this gives me y.
Right.
I want the y went through this. So that's y times this. So y times that mess, which is my output. Whatever I want to call this Larry. Right?
John Wilma.
So, prefer Wilma? Okay. You know, maybe we'll do Barney, but then the whole thing will turn to rubble.
Very nice.
You stepped in that one.
Yeah, you did.
So, right, this whole middle part becomes this divided by this. Do we all agree?
Yes. Most definitely.
Okay. This divided by that 1 plus h2, h3, h1 over 1 plus h1. With appropriate s's in there. We're almost done, aren't we?
I have just one quick question.
Sure.
The h2, h3, h1 over 1 plus h1y, the very first line,
Yes.
where's
that's
that
correct.
multiplication coming from?
Because, well, I've erased it now.
Yeah.
But it was, you know, remember the loop came from
They were in parallel.
my whatever y. No, but they're not in parallel. They were in a loop. It was
Feedback.
h1 over 1 plus h1.
Yeah.
And it fed back into
Oh.
h2, h3. And then it came in negative into here.
I've got my arrows wrong on here. That's why I was confused. Okay.
Right? So y times this gives me what gets subtracted.
Okay.
Don't think I remembered that. I actually just reread it from the equation. Once you get used to it, you just notice this is your feedback gain, this is your system matrix. So it's always system matrix over 1 plus feedback times system.
That only works for negative feedback, though. You get the 1, right?
No, if you do positive feedback, it becomes a minus.
It just becomes, oh, okay.
Right? So if you think about it, you know, if I've
It's just
got
the gain
something
of
on top X, if I've got negative feedback, I have this. If I've got positive feedback, I've got this.
This is just the negative.
So if X is some small number, or they even say this, say X is like magnitude 0.6. I've got 0.6 over 1 minus 0.6. It's bigger than 1.
Okay.
Right? Whereas this one, if it's 0.6, I have 0.6 over 1 plus 0.6. It's always smaller.
Gotcha.
So this one goes smaller and smaller. This one has the potential to get bigger and bigger. So therefore, this one is bad. So if you ever tell anybody they're wrong, just say it's more stable if I tell you you're wrong. Because positive feedback is not stabilized. Yes, they love that when you say that. And I can mathematically prove it. So you suck. You know? It gives you an excuse for it. Don't really do that. That's just a joke. But it's funny to think of as it goes. Okay, so far so good?
Yes.
Can anybody tell me how I can get rid of these?
Right there, and they're, oh, wait, they're not in the feedback loop. Sorry.
No, they're just, this is called feed forward. Because I fed forward.
Yeah.
Well, but see, notice this is Wilma times H4 and this is Wilma times H2. So
Wilma times the addition.
Wilma times H4 plus Wilma times H2,
Pull out the well.
right? That's what you're getting here at that, after the summation junction. Pull Wilma out. That must be your system.
Apparently that's a lot easier.
Input times system gives you output. That's what we got in frequency space. So that tells you this whole thing reduces down to just sum them. But now they're in series, right? So if they're in series, what do I do? Just multiply. And you could put in whatever the H values are, right? So you got those from something, whatever it is. Could be an equation for a motor, it could be a control law, it could be whatever mathematical description you want. You now know how the entire system works. Once you get used to how these things are manipulated, you'll notice it always follows these patterns. Sometimes people call rules or whatever. It's just algebra, just turned into graphical form. Just pictures are easier to deal with and funnier. So
That's a big box.
I agree, but would you have rather done that by actually doing all the necessary convolutions and everything else to describe how those systems interact? Yeah, that would have been ugly. But this was, I mean, actually, relatively speaking, pretty painless, wasn't it? And you got a fairly complicated interaction. This is why I submit to you, doing this in Laplace space by graphical techniques is much easier.
So something like this is better represented in LabVIEW than MATLAB because the graphical interface.
MATLAB has a graphical interface. It's called Simulink.
Yeah.
And it's had it for decades. The reason why I don't usually introduce it in like 535 and stuff is because in 535 you're supposed to learn the algorithms that manipulate rather than the graphical interface to then use those. But you can describe those algorithms as a box. So you can write your own algorithm in a box for whatever those are and you get your inputs and you get your outputs. So if you think like you generate splines, I give you a series of data points, it goes through the spline calculator and it gives you the spline equation out. So it's no problems. So you could rewrite all your code in that sense. And that's where we get like flow charts and the rest of those. And you can now manipulate your functions as they work on data. They can input and output. It's just a different way of handling it. But completely analogous. So either one you like.
Perfect.
Good?
Yep.
Awesome. So next time we'll go into a little more advancing. Maybe we'll take a full example from start to finish.
Listen to that.